In the last section, we segmented a large LAN or network into smaller collision domains using bridges and switches. Both of these Ethernet devices operate at the data link layer and use Layer 2 or MAC addresses to help manage and control traffic. Now we'll take a closer look one layer up in the stack at Layer 3, the network layer. We'll examine the differences between Layer 2 and Layer 3 and introduce you to routers, the network devices that operate at Layer 3. Note that either of the two symbols shown on screen can be used to represent a router. The symbol on the left is used to represent a small router. The symbol on the right is more frequently used to represent a router in network diagrams. We'll use this symbol to represent a router in the rest of this course. As in the previous section, we will use Ethernet-based LANs and TCP/IP-based protocols in our examples, but you should keep in mind that other technologies and protocols do exist. You'll remember from the last section that each network interface card, or NIC, has a Layer 2 or MAC address assigned by the manufacturer. Devices might have multiple NICs or network interfaces if they require connections to more than one network, but every MAC address must be unique. Since these numbers are either assigned sequentially or generated randomly, there is no logical way to group them. Remember also from Section 2 that the first 3 bytes of the MAC address comprise the Organizationally Unique Identifier, or OUI, that every Ethernet equipment manufacturer is assigned by the IEEE. Here you can see that the network devices have NICs from different manufacturers, since the OUI is different in each MAC address. In the previous section, you became very familiar with the actual format of unicast, broadcast, and multicast MAC addresses. Now that you're familiar with what MAC addresses look like, we're going to make our diagrams a little easier to read. Going forward, we'll use just the last byte of each MAC address to represent the full address. As in the previous section, we'll continue to use the letters DA to label the destination MAC address and SA to label the source MAC address. If two devices on the same segment want to communicate, they must use MAC addresses. In addition to a Layer 2 address burned into it by the manufacturer, each NIC or network interface also has a Layer 3 address assigned to it by the network administrator. Remember from Section 1 that the Layer 3 address is analogous to the street name and house number that the post office uses to deliver mail. Just like a residence, a Layer 3 address also has 2 portions, a network number and a device or host number. The network number is analogous to the street name, and the host number is analogous to the house number. Network administrators assign Layer 3 addresses, specifically the network number, to all devices on a network in order to introduce order into a network. Layer 3 addresses provide a way of grouping network devices. For instance, Layer 3 addresses could be assigned to group network devices by building, by floor, or by functional group. On screen, you can see we've assigned Network 1 to this group of PCs. Notice that all the PCs connected to this switch use the same network number. We've also assigned unique host numbers to each PC. Note that in this section, we'll represent Layer 3 addresses with the network number.host number format shown on screen. But as with the MAC addresses shown here, this is a simplified format. Here is one real-world example of a Layer 3 address and a Layer 2 address contrasted with the shortened formats we'll use in this section. As this section continues, we'll see how Layer 2 and Layer 3 addresses are used to route data within a network and across networks. In the previous section, we defined the term collision domain as a group of devices competing for network access. Bridge networks had collision domains with many devices. With the introduction of Ethernet switches, a collision domain might contain only 2 devices, an end-user device and an Ethernet switch. A collision domain is a Layer 2 domain because bridges and switches isolate traffic into separate domains based on the Layer 2 addresses in each frame. Moving to Layer 3, we find a similar concept. Layer 3 domains are called broadcast domains. A broadcast domain is the group of devices that can be reached by sending a frame addressed to the broadcast MAC address. You might remember we discussed broadcast MAC addresses in Section 2. The real broadcast address is shown on screen, but since we are using shortened MAC addresses in this section, we'll just use FF to represent the broadcast address right now. A broadcast MAC address is the address a device uses to send data to every device within a LAN, either directly or by way of a bridge or switch. When a bridge or switch receives a broadcast frame, it must forward it out every one of its ports. Each device in a broadcast domain has the same network portion of their Layer 3 address, and each has a unique host number. In the network shown on screen, the broadcast domain consists of all PCs connected to the Ethernet switch. If PC 1.2 sends a Layer 2 broadcast, the switch forwards this frame to all other PCs. Now let's take a closer look at how devices communicate using both Layer 3 and Layer 2 addresses. If PC 1.2 wants to send data to PC 1.8, it first determines whether the destination PC resides on the same Layer 3 network or broadcast domain. The PC looks at the network portion of the destination Layer 3 address and compares it with its own network number. If the Layer 3 network numbers are the same, the two PCs are in the same broadcast domain and can communicate directly. If the two PCs aren't on the same network, they can't communicate directly and will need the help of a router, which is a Layer 3 network device we'll get to shortly. Next, even though PC 1.2 already knows 1.8's Layer 3 address, it must determine 1.8's MAC or Layer 2 address. It does this by sending a Layer 2 broadcast frame to every device in the broadcast domain requesting 1.8's MAC address. This request has a special format, which includes the sender's MAC address, the sender's Layer 3 address, the target Layer 3 address, and 00 for the target MAC address, indicating that the target MAC address is unknown. This broadcast is like yelling so that everyone can hear you. PC 1.8, are you out there? If so, what is your MAC address? All devices in the broadcast domain receive the broadcast frame and look to see if the request contains their Layer 3 address. Only the PC with the specific Layer 3 address in the request will respond. All the other PCs will ignore the request. In this case, PC 1.8 inspects the request and sees that it is the intended recipient. PC 1.8 creates a reply to let PC 1.2 know its MAC address. In the reply, PC 1.8 is now the sender, so it includes its MAC address as the sender's Layer 2 address and its Layer 3 address as the sender's Layer 3 address. Notice that the sender's Layer 2 and Layer 3 addresses always correspond to the device generating the request or reply. The sender's Layer 2 address will always match the Ethernet frame's source Layer 2 address as well. PC 1.8 then sends the reply back to the PC that requested it. Now the two PCs can communicate using unicast Layer 2 frames. These unicast frames are like two people whispering to each other so as not to disturb others. Now you might be asking yourself, if the sending device already knows the destination device's Layer 3 address, why does it also need the Layer 2 address? Why not just communicate using Layer 3 addresses? The answer to that can be found in the concept of layering. Remember in Section 1, we introduced the network stack? In that section, we discussed how data moves down the stack of the sending computer and then up the stack of the destination computer. Each layer on the sending computer communicates with the corresponding layer on the receiving computer. When the data arrives, the receiving computer verifies that the data reached the correct destination before removing the header and moving up to the next layer. The data must go through each layer and it cannot skip layers. If we look at the model again, you can see that even though the sending device might know the destination device's Layer 3 address, the two devices must first communicate using Layer 2 addresses, since it is the last header and address information the sending computer adds, and the first header and address the receiving computer encounters when the data flows back up the stack. In networking, the process of using Layer 3 addresses to determine Layer 2 addresses is known as address resolution. In TCP IP-based networks, the protocol that manages that is called, fittingly enough, the Address Resolution Protocol, or ARP. ARP maps an IP address, which is a Layer 3 address, to a Layer 2 address. Other non-TCP IP protocols use other protocols to resolve addresses. On screen, you can quickly see that very large broadcast domains might cause network performance problems due to the increase in the sheer volume of Layer 2 broadcast data flowing between devices. To solve this problem, in much the same way network designers broke up collision domains into smaller segments, they break up broadcast domains into smaller separate networks. But just like it wasn't possible to break up collision domains into smaller segments before switches were developed, breaking up broadcast domains also required a new network device, called a router. Where switches allow communication within a broadcast domain, routers allow communication between broadcast domains. Each broadcast domain then becomes a single separate network. Within a group of interconnected networks, each network or broadcast domain must have a unique network number. Just like a street name must be unique within a city. Each host on a network must have a unique host number, which is similar to a house number. Just as the same house number might be found on different streets, the same host number can be used on different network numbers. Here you can see that we have segmented our large network into 3 smaller broadcast domains or networks. Within each network, each device has a Layer 3 address consisting of its network number and unique host number within that network, and each device has a Layer 2 or MAC address. In addition, notice that each port or interface on the router also requires a Layer 3 address and an associated Layer 2 address. A router is a Layer 3 device and forwards data from one network to another. To facilitate communication, routers must know how to reach other networks. Routers can learn this information dynamically using routing protocols, such as the Routing Information Protocol, known by its acronym RIP, or the Open Shortest Path First Protocol, or OSPF, the discussion of which is outside the scope of this course. You can also statically configure this information on the router. With either approach, a router stores this network location information in a routing table that includes all possible destination network numbers and how to reach them. Each entry in the routing table includes the destination network number, the next hop along the way to the destination network, and which port or interface on the router should be used to reach the next hop. The next hop address either indicates that the destination network is directly connected to the router or provides the address of another router on a directly connected network. When a router receives a packet, the router uses the routing table to make intelligent decisions on where to send the packet next. In this example, the router connecting Network 1 and Network 2 receives a frame on port 1. First, it examines the destination MAC address to see if it is the intended recipient. Because the frame is addressed to the router, it strips off the Layer 2 frame to inspect the Layer 3 addressing. The destination address is 3.2, so the router consults the routing table to find out where to send data for Network 3. It determines that it needs to send the packet to the next hop router, which is address 2.2 out port 2. At this point, the router adds a new Layer 2 frame, including the source MAC address and the next hop router's MAC address. We will go into this process in greater detail in the next section. Notice that this router only knows the next step or next hop to the destination network. It does not know the complete path. Through individual routing decisions made by routers at each step along the way, the data eventually reaches its destination. What if the router receives a packet destined for a network not in its routing table? Here we see that the router has received another frame on port 1. Since the frame is addressed to the router, it strips off the Layer 2 frame. In this case, the destination address is in Network 5, but there is no entry for Network 5 in the routing table. If the router does not have a route for a destination network number, it will drop the packet and might send an error message to the sending PC. To avoid this situation, many network administrators configure routers with a default route that tells each router which way to route a packet if it encounters one with a network number it doesn't have listed in its routing table. In this example, we've added a default route to the routing table that specifies that data addressed to any unknown network should be sent to the next hop 2.2 out port 2. The router adds a new Layer 2 frame so it can send the data to the specified next hop router. Perhaps the next hop router will have a route to Network 5 in its routing table. Now that we have 3 separate networks and 3 separate broadcast domains, Let's see how data flows from a PC on one network to a PC on a different network, focusing on Layer 2 and Layer 3 addressing. We'll also see the major difference between Ethernet switches and routers in action. In this example, PC 1.2 wants to send data to PC 3.2. First, the application layer sends the data down to the transport layer where a Layer 4 header is added. Next, the transport layer sends the data down to the network layer, which adds a Layer 3 header. This Layer 3 header includes the source and destination Layer 3 addresses. Remember that in this section, we're using a simplified format, network.host, rather than a full IP address. Moving on to Layer 2, things get a bit tricky. Before the source PC can add the Layer 2 header, it must determine if the destination PC is on the same network by examining the network portion of the destination Layer 3 address. Let's focus on Network 1 for a moment to see what happens within this network. Throughout this extended example, we'll focus our attention on specific areas of our network. We'll keep a thumbnail drawing on screen with a highlight on the portion we're currently focusing on to help you keep track of where we are in the larger network diagram. In the previous example, when PC 1.2 wanted to send data to PC 1.8, the sending PC's network portion was the same as the destination PC's. Therefore, PC 1.2 simply sent out an address resolution request to determine PC 1.8's MAC address. Remember that an address resolution request is sent to the broadcast MAC address, so all devices in the broadcast domain receive this request, including the router. Since the Layer 3 address in the address resolution request does not match the router's Layer 3 address, or in the case of IP networks, the IP address, the router simply drops the packet. It does not forward broadcast frames out the other ports, hence reducing network traffic. PC 1.8 is the only device that responds to this address request. After receiving the response, PC 1.2 will fill in the source and destination MAC addresses and transmit the frame. In this example, however, by examining the network portion of the Layer 3 address, the sending PC can determine that the destination PC is not on the same network and that the two PCs cannot communicate directly. In this case, the sending PC sends the data to the nearest router, also known as its default router or default gateway. If the source PC already knows the default gateway's MAC address, it skips the address resolution process and sends the packet to the router for further processing. If it doesn't know the router's MAC address, it sends out an address resolution request to determine it. The router will respond with its MAC address. Then, PC 1.2 will be able to address its data to the router, so that the router can figure out how to forward it on to Network 3. A default gateway is different from the default route described earlier. A gateway is a device, such as a router, which serves as a door or an access point to another network. End-user devices, such as PCs, send packets to their configured default gateway when the destination network number is not the same as their network number. A router, on the other hand, does not have a default gateway configured since it is the door to other networks. Instead, a router uses a default route to direct traffic if it encounters a network that is not in its routing table. You might be asking yourself, how does the PC know the Layer 3 address of its default gateway? This address is either configured by the network administrator or learned dynamically. However, as when sending to any device, the sending PC needs to determine the default gateway's Layer 2 or MAC address using the address resolution process before it can send the packet. Once the PC determines the default gateway's MAC address, the PC adds the Layer 2 header using the router's MAC address for the destination address and its own MAC address for the source address. If you remember our discussion of addressing in Section 1, the Layer 3 address identifies the final destination. The Layer 2 or MAC address identifies the stops made along the way to get to the final destination. Layer 2 addresses change with each stop along the route to the final destination. Now that PC 1.2 is ready to send its data, let's take a look at the Layer 2 and Layer 3 addresses that are included in the frame and the encapsulated packet. See if you can identify each of the data elements on screen by dragging a label from the Possible Labels box to the appropriate empty label on screen. Incorrect matches will bounce back. Well done! You have correctly identified each of the addresses in the data. Remember that the destination layer 2 address is the data's next hop, in this case the default gateway. On the other hand, the destination layer 3 address is the data's ultimate destination, in this case PC 3.2. Click the Continue button when you are ready to see what happens next. After layer 2 encapsulation is complete, PC 1.2 converts the data to ones and zeros and sends it over the wire. The Ethernet switch connecting the source PC to the router receives the frame, examines the layer 2 destination MAC address, and looks for a match in its MAC address table, which, on a switch, is commonly called a forwarding table. If the switch does not find the layer 2 address in its table, it will send the frame out all ports except the one it came in on. In this case, the switch finds a matching entry for the layer 2 address, so it only forwards the frame out the port specified for that address. Notice that this layer 2 device did not look at the layer 3 header or change the layer 2 source and destination MAC addresses. Next, the router receives the frame and examines the destination MAC address to see if it is the intended recipient. If so, the router strips off the layer 2 frame and examines the destination network portion of the layer 3 address, which, in this case, is network number 3. The router looks in its routing table for this destination network number. The router finds network number 3 along with the layer 3 address of the next router in the path to the destination network. Next, the router adds a new layer 2 frame, including the source MAC address and the next hop router's MAC address. If the router does not know the MAC address for the next hop, it performs the address resolution process to determine the MAC address. In this case, the MAC address for 2.2 is BB. Notice that the source layer 2 address is now AA since the data is being sent on a different port. Since a router is a layer 3 device, when it receives a frame addressed to itself, it can strip off the layer 2 frame and examine the destination layer 3 address to make an intelligent routing decision. The router cannot change the destination or source layer 3 addresses. However, a router changes layer 2 addresses with each hop. In contrast, a switch can access layer 2 addresses to forward frames, but it cannot change those addresses, and it has no access to layer 3 addresses. So back at our example, the Ethernet switch connecting the two routers receives the frame. Our data is halfway to its destination. Let's zoom in on network 2 and see what happens there. The switch examines the layer 2 destination MAC address and looks for a match in its MAC address table. Once it finds a match, it forwards the frame out the correct port. The next router repeats the strip and lookup process. First, it checks the data's destination MAC address. Then, it strips the layer 2 frame and examines the destination layer 3 address. But this time, the destination network is directly connected to the router, and the routing process is complete. At this point, the router determines PC 3.2's MAC address and adds the layer 2 header, including the appropriate destination MAC address, and the source MAC address for the port on which it is sending the data. Then the router transmits the data. The switch connecting the router to the destination PC uses the destination MAC address to forward the frame to the correct PC. When the PC receives the frame, it first examines the destination MAC address. If it is the PC's MAC address, the PC strips off the layer 2 frame and examines the destination layer 3 address. Again, if it matches, it strips the layer 3 frame and examines the layer 4 header. This process is repeated layer by layer until the application on the PC receives the data. Our data's journey from PC 1.2 to 3.2 is complete. In the learning activities at the end of this section, you'll have a chance to test your knowledge of layer 2 and layer 3 addressing and how data is routed from one device to another across multiple networks. In our previous example, the routers interconnected Ethernet LANs, which use the same layer 2 frame format. What if there is a WAN between the two routers? Or a different type of LAN? Different layer 2 technologies, such as Ethernet, FDDI, ATM, or frame relay, have unique layer 2 formats. Since a router strips off the original layer 2 frame, performs a route lookup, and adds a new layer 2 frame, routers can also connect different types of layer 2 networks. Here you see Network 2's data link is now using Fiber Distributed Data Interface, or FDDI, which is a standard for data transmission on fiber optic lines that can extend in range up to 200 kilometers or 124 miles. When the router receives data from Network 1, it strips off the Ethernet frame, performs a route lookup, and determines the next hop address. After determining that the data will be sent to Network 2, the router adds a new Layer 2 header and trailer using the FDDI frame format. Like the Ethernet frame, the FDDI frame includes source and destination MAC addresses. However, notice that the FDDI frame format shown on screen is very different from the Ethernet frame format. Here's a chance to test your knowledge. As you saw in this section, different devices need to access different layers of data in the 5-layer model in order to send data to its destination. In the simplified network